All right. Can everybody see my Jupyter Lab instance here? So I posted on Slack the URL for the repo. So I suppose everybody just clone the repo, open the terminal as you guys are seeing here, and just basically git clone the tutorial like this, right? I have already done. So on the left, we're gonna have then generated a intro HDF5 folder. Let's go inside. And then we have a notebooks folder. Let's go inside that. And then we have two notebooks. So I have separated this next tutorial into two parts. One is I have the intention to walk you through the HDF5 data model. And the idea is to make you comfortable with that file structure. And the second one, we're gonna do something more interactive and practical. We're gonna reduce the original data files that we downloaded from NSIDC. And in particular, we're gonna be dealing with the ATL06 data product, but this can be extended to any other product. And as Jessica and Amy showed in the first tutorial today, and we tried to put this all in a logical order, right? The first step you wanna do is to get the data files from wherever they are. For example, NSIDC. So we got that in the first tutorial today. Now, the second step you wanna do is to actually extract the data out of those data files and perhaps prepare that data set into a more practical and useful, smaller chunks of files or subsets of data for your analysis. And that's what we are doing on the second tutorial. So let's go and click on the intro HDF5 notebook there. And I'm gonna maximize my working area here. Is the font size okay?
Yeah, that looks good, Fernando.
Okay, so let me just try to do one little thing here. Okay. Okay, so introduction to the HDF5 data model. So what is this HDF5, right? The HDF5 stands for Hierarchical Data Format version 5. It is a file format optimized for numeric data, right? So while we have all the kind of file formats optimized, for example, for ASCII strings, in this case, we are interested in optimize the performance of numerical values. So this HDF5 has been developed for that purpose. It is a hierarchical structure to store information. So inside an HDF5 file, what we have is actually like in our operating system, a file structure. So what we do, we organize different sets of information into folder-like objects. And we're gonna see about that. And that's very easy to, very convenient for organizing and for accessing all these different pieces of information. So it is a self-describing container. Like others, this is not the only one. When we say self-describing, means that we, in addition to the data, we have metadata, which is information about the data themselves. And this is very useful, for example, for some applications that will access the file, and the first things these applications will read out of the file is the metadata to know what to do or how to access the actual underlying data. Now, HDF5 is also a library. So meaning that together with this data file structure, they ship to you some high-level tools. We're gonna see some of those. In particular, they are command line tools, and they are very useful. Okay, so what's awesome about this kind of data structure? From the user side, this is a high-level interface. That means that the user, and when you type some code in Python, R, MATLAB, whatever is your language of choice, you're gonna access the data very easily. Now, from the machine side, the data is in binary format and it can be further compressed. So it's a low level, and that makes it very efficient for processing. HDF5 in particular is very fast at reading, pulling out data from the files and reading into the files. That makes it very good for high performance computer systems. And this was the original idea of use for this data model. And lastly, and this is also very important, in storing data in HDF5, like all the models as well, we can read and write in chunks. That means that we don't need to load the entire data set in memory, right? Our algorithms are pulling chunks of data one at a time into memory, processing those and saving back to disk. So we can deal with much larger than memory data sets. Okay, so why NASA and many other organizations have chosen to distribute their data in this format, right? It's popular. It turns out it's very popular. So here we have, for example, who uses HDF5 as their underlying data structure. For those who use MATLAB and they are used to these .m files from MATLAB, they are nothing else than HDF5 files that MATLAB then wrapped around their own interface. NetCDF4, this is an extremely popular format for climate data, in particular in the atmospheric and oceanographic sciences. So NetCDF4, when they transitioned from NetCDF3 to 4, they realized that they could not do better than what HDF5 has done at the time, and they didn't want to reinvent the wheel. So what they did, they took the HDF5 data model as is and put on top of it a NetCDF4-like interface. So the users did not know any difference in accessing the NetCDF4. But on the code side, on the machine side, it is an HDF5 what is performing, allowing you to organize your information. Also, the popular Keras built on top of TensorFlow saves machine learning model weights to HDF5. And finally, that's the format ISA2 comes in. So we need to be comfortable with it. Okay, we have now here a set of small steps. It's mostly the idea so you feel comfortable with operating with these files. Let's start just by writing some data. We're gonna create some data on HDF5. Here in this cell that I just clicked, I just called NumPy and created 3 1D arrays, X, Y, Z, random numbers. And this is, I make a note here, one library to operate with HDF5 within Python is called H5Py. It is a very simple library, very easy to use, and it mimics the original C interface to access this HDF5 library. So, okay, this is how we create an HDF5 file. We call H5Py file, the name of your file. We should add write. We can write, read, or append. And we simply use that F as a dictionary. F is our file, and we are saving X to something that we want to call whatever we want. In this case, I'm calling X, Y, and Z. That's simple. Okay. So that file was created. It was open, written, and closed. On the next cell, we are going to, through the command line, use the ls command and see if we have any .h file created. And there you have, we have a myfile .h5, okay? So as I mentioned to you, the HDF5 comes with some command line tools. This is very convenient because we can inspect HDF5 files. We can do some operations with these files without having to write a single line of code, just through the command line. So this is one of those tools. It's called H5ls, trying to mimic the ls command on the terminal. So we can do on the terminal, that's why we have an exclamation point in front of it, H5ls and our file that we just created and see what comes out of it. And it displays for us on the terminal the content of the file. We have an X, Y, and Z. These are data sets, and they have 100 length each. We're going to see more of these tools in a little bit, so that is the simpler of all. So we wrote data to HDF5. Let's now read data from HDF5. We open the file in a similar way, my file, and then we append read instead of write. And here there are 2 ways we can interact with this file. One is calling this bracket notation, which what it's doing is loading that particular variable X into memory and return to us a NumPy array. The other is just calling the name of the variable or the group without loading into memory. So what this is returning is a pointer that points to a block on disk where that data is stored. In doing this, we can access some information about that data in cases that where the data is very large and we don't need to load it. So let's hit enter on that cell and see what comes out of that. So I'm printing a few of stuff regarding our X and Y variables. So X is a 1D array and is a NumPy array. Y is a non-disk. So it will show you that it is still an HDF5 data set object, but you don't have the values on it. And here you have the type of objects they are. X is a NumPy, Y is an HDF H5Py class. However, here's what I said. We can access, for example, the shape of these variables, both of them, and they come up exactly the same. So our code can interact with these variables for some operations in the similar way, even though one is loaded in memory, the other is not. What else can we do? We can append data to an existing data file. This is what we are doing here. Now we open the same file and now we put A instead of read or write. And this is important. If you forgot to put append and, for example, leave the write in there, what's going to happen, this step will overwrite the file that you already had. Okay, so either put append here or read if you don't want to do anything with the file. And here we're going to save data in a different way. So we had, remember we had created the three data arrays, right? X, Y, and Z, same length. So we're going to take now the Z variable. We're going to do something here, Z to the square, and then we're going to Z reshape it. And instead of 1D, we have a matrix now 10 by 10. But we want to, I mentioned to you that we have like a folder-like structure. So we want to save this guy on a set of folders. So we're going to create a folder called path, a folder, a subfolder called to, a subfolder inside of to called data, and then we're going to name our data set. Let's hit enter there. Name already exists. Yes, okay. So this is what happened. Let me, if you are getting this problem, it's because the file was already in there. Remove my file there. Let's go again. Probably I save it in the beginning. So we're gonna do. So let me see what's happening here. Yeah, let's remove that guy. Yeah, in the previous tutorial, I had a remove file in case we were repeating this. So let's go again here. So we have our variables. It should be okay. Yes, there is okay. Our file is created. This guy is created. We're reading our file. Okay, there we go. Okay, so probably the file was there in the beginning and we were trying to write or create a variable that was already in the file, right? So it tells you this variable already exists. You cannot overwrite it, right? So two things to note in here, very important. So path, to, and data are what we call groups or folders. Vect and math are the actual data sets. So this is a very important distinction. Groups and data sets, these are the two kind of object stores that we put inside an HDF5 file. So this is another command line option to inspect the file. We have used before H5LS. Now we add to it an -R, and what we are getting is a recursive inspection on the file. So it shows us not only the XYZ variables, but it shows us the path2 data, and the math and vect variables as well. This is very, very cool command line in there. And it tells you these are groups, these are data sets, and these are the dimensions, right? So note that we haven't written a single line of code, and we are already inspecting the file. So this is another command line tool. As I mentioned, the HDF5 format allows us to have metadata and data. So let's add our own metadata to this file. First of all, before we do that, let's inspect the metadata that is created by default. And here we have another command called h5dump -h means header. Show me the header of this file. And this is how the metadata that is created by default looks like, right? Remember we had groups, path, group 2, group data, the type of data that they are capable of holding. And we have our vect and math, these are data sets, etc., etc. So, okay, a little bit is added for you by default, but what if we want to add more information? I want to distribute my files, and I want to have, you know, my name in there, my email, perhaps the date the file was created, or the version. So the way we do this, again, append, because we are going to modify an existing file. We are going to pull a group and save it and have it as a variable called G, which is a reference to the group inside the file. And we are going to pull a data set, which is not, we're not loading this data set in memory. Recall, I'm not using bracket notation. So I'm having a reference to the data set. And with those references, one for the group and another for the data below, I will add something that's called attributes. This is exactly a Python dictionary. An attribute, the name that of the field that I want to put some information into, and then my information. So that's simple. I added that information there. So now let's look again at the header of that file and see how it looks like. And we see that we have a much larger header that you have. So I'm putting this header in here, or -H is in the previous case, to avoid printing on the screen the actual data, because you can do that as well. If you don't put anything, h5dump will show you the header plus the data on each of these objects. But since we don't want to pollute the screen, just stay with the header. Otherwise, it will fill in the entire terminal with data. Okay, more high-level tools. This is, remember the use of this magic bash. So this is like running on the terminal. We have something called h5copy. h5copy allows us to pull one variable or field from one HDF5 and copy to another HDF5. If that file does not exist, it will create it. If it exists, it will append the variable to it. Very convenient. So far, we haven't written a single line of Python code. So I'm going to take input my file h5 and output my file to source, the field that I want to copy, X, and the way I want to save it. I want to save it X as well. And on the second line, I'm doing the same, but here I'm copying from file 1, that guy that lied inside path2 data math, and I'm going to copy it just as math. And then I'm going to check out if those files were generated, and I'm going to do h5ls on the second file, the file that I just created by copying to inspect it. Enter, and here we have the original my file 2, and the my file 2 now has two things in it. One data set called math 10 by 10, and another called X 100, one dimensional. Very cool. So one last command line. There are many other tools from HDF5, and this is h5diff. This allows us to check differences between two HDF5 files. Let's see what it does when we ask the difference between my file and my file 2. Here you have file 1, file 2, and with X, it shows you what elements are in both files, or only on file 1 or only on file 2. So this is the root group, exists on both files. Dash mat only exists on file 2. All these groups path only exist on file 1. Dash X exists on both files, and so on. Very cool. Okay, now we leave the command line and we go to Python, because we actually are going to work with Python. So how do we read an HDF5 on a Python script and inspect it very quickly? So again, we use this h5py library. We load a reference to that file, and all this reference is a dictionary, is a Python dictionary. So we can treat it as such. Now we're going to print the keys of that dictionary. And that shows us that this F dictionary, which is pointing to the file, has something called path, something called X, something called Y, and Z on the first level. It doesn't go recursively, right? If you want to go recursively and traverse the entire structure of your data file, then we have to make a tiny function here, which actually will walk through the file. And this is also Python. Let's print it, and there you have it. It shows us very nicely the attributes, remember, that we put in there. It shows us all the groups, path to data, map, the data set with its own attributes and all the other elements. Very cool. Now, note that I didn't open this file with the block opening, like with file open SF. That takes care of closing the file for you. Now, another way of opening a file without closing it, because you want to do a further of operations along the code, is doing it this way. And then in the end, you need to remember to close it. F closed, right? So now the file is, the information was flushed to disk and is not available to us anymore. So other things we can do more advanced with an HDF5 structure. We can create what's called extendable data set. And this is how ISA2 variables come. That means that we can define a particular structure initially, and later on allow users to keep adding data or growing that structure on a particular dimension that we define. So here, instead of using this dictionary style, we're going to use a function from h5py called create dataset. We open our file, my file, sf create dataset. We have a pointer to that, and we are going to give it a name. In this case, I name it grids, and I'm going to start with a shape called 10, which is 10 by 10 by 5. And then I'm going to define what's the max shape that this structure can take. And I'm going to limit the dimension, the first and second dimension, to 10, the original. And I say, I don't want this to grow on any of these dimensions, but I'm going to allow this structure to grow on the third dimension. So I add none. You define the data type. This is important. HDF5 allows for chunking operations. That means your code and the routines that, within the h5py library, if you have chunk set to true or defined to a specific size that you can do, so these routines will pull out chunks of data, do something, and push the data back to disk. And last, we can add compression, as I mentioned. So this way of creating the data set is a better way because we can define and take advantage of all these optimizations. So our data now on disk will be compressed. So let's check. We have created, let's check from the command line. Here it is, grids. This is our newly added data set. It's a data set and it has 10 by 10 by 5. However, it has an infinite statement here. And that means that although now it has a 5 length, this dimension, it can grow indefinitely. So if you inspect ISA2 files, most of the variables will have this in it as well. So just for fun, and I don't want to spend too much time on this tutorial because the second one is a little bit more interactive and practical for you guys. So from now on, I'm going to go all these steps one by one. So I'm going to just create a set of grids in here at random. So I have 5 grids of 10 by 10, and this is a list of grids. Let's suppose we are creating some data, and I want to open a file that already exists and append those grids to that object called grid. And this is what I'm doing here. I open as append, I pull out the object or a group or think as a folder called grid, and then I can operate with that guy as if it were an array, because it is an array. And I just iterate over each of my 5 grids and save one at a time. Okay, now we save our grids. How about we have, you know, a data cube on an HDF5, and I only want to pull some slices from that data cube. So you can use something else here, which is the famous Python fancy indexing. So now I'm opening for read, note here, the file. I'm gonna call this grids group that I already know contains, you know, 5 grids. And I'm gonna pull on the 3rd dimension only the slice 0, 2, and 4. These are 3 grids out of 5 that you have. And it returns to me a structure which has 10 by 10, the size of each grid, and 3 in the 3rd dimension. Okay, just quickly, are those really the grids that we generated? Yes, here it is, 1, 2, and 3 random number grids, okay? All right, with that more or less concludes, you know, the very basic steps to manipulate HDF5 files. So then the question, and this is something more recent, I had to update the tutorial compared to last year, is what about the cloud? We are working on the cloud right now, and cloud is becoming more and more popular within the science. Now, it is already very popular in industry, for example, but science takes a little bit more time to adapt to these technologies. So it turns out that the HDF5, because it was you know, designed 20 years ago, is a very mature and solid project. Back 20 years ago, we didn't have cloud computing services as we have today. So they had to adapt to cloud computing. So there is something that the HDF group, the group that actually, you know, handles and works on the HDF5 data model, they come up with, it's called highly scalable data service. And I would not go in much details on these cloud storage formats, but just you can come up on the tutorial here, and I have further information down there. But what this does is an mapping, an interface that will map the HDF5 array that your application sees to what the cloud, to the way the cloud store this data object, which is called a cloud store object, right? The cloud storage system does not care if whatever you are putting in there is an HDF5, a NetCDF, Excel spreadsheet, or whatever. They're just going to store that as object. But your application on this other side, if you pass an URL that points to an Amazon bucket, it wants to open that object as an HDF5 file. So this is what this guy does. So that is a workaround on the limitations of HDF5 for cloud storage format. Okay, one last comment here. So it turns out that within the Python community, we have something that is more optimized for cloud-oriented storage and operation stuff, which is called the ZAR library. This is a newcomer data model, and it has like less than 5 years of being developed. So it's a very young project yet. And basically, without going in details, I'm just going to read to you here. What they did is they said, well, the HDF5 data model is awesome. So they took all the capabilities of HDF5. So ZAR offers you pretty much everything I showed to you here. And on top of that, they added a few more capabilities. So what are those capabilities? What these guys did basically said, how about if instead of saving everything on a single structure called HDF5, we just take every single chunk of information and store it as a single individual file. And then we take the metadata and save all the metadata into a single file, which is an ASCII file, text file. So we have many chunks of data in binary format as individual files, and a single centralized metadata as a JSON file. So with that, which is very simple actually, they solve 2 fundamental problems that HDF5 is trying to overcome. One is they can do this mapping between the cloud storage objects and your application straightforward, out of the box. And the second, they can do parallel writings on the same overall data set, trivial, because now the parallel writing here is happening on individual chunks of data as individual files, so there are no conflicts. Anyway, here I have comparisons with HDF5, differences with HDF5, so on and so forth. All right, so As a bonus, let's jump to the bottom and then we go to the next tutorial, which is, I don't want to run out of time. If you like to interact with your data file on a graphical user interface, well, the HDF5 group has a very nice application called HDF View. And basically allows you to do, to visualize the data on a tree-form format, even display some, matrices here. This is a slice of a matrix, and do some other operations, copying, like I showed to you, and checking differences between files, all on a graphical user interface. Okay. All right, let's leave it at that. And let's now switch to the next tutorial. Of course, you can come back to this tutorial and you can ask me questions. I will be available on the office hours, and you can ask me. Okay, let me maximize the area here. Okay, the idea here is I'm going to show to you now how we can, reduce some of these original ISA2 data structures to something, more tractable, something that we are more comfortable with. And everything I'm going to show you here in terms of strategy is actually a real use case. It's not a toy example. This figure here is this kind of stuff that we do here at JPL. You are seeing here the processing of the full ISA1 archive plus ISA2, all the data that we had available at the time we made this figure, which was a few months of data. So this is the way we treat data here at JPL. Okay. Let's start clicking the cells here. And in the beginning of this tutorial is mostly a reminder of what you already saw. This is the way ISA2 data is organized spatially, right? Each file is a granule, which is a tiny segment of a single flight. And then we gather a bunch of granules and we separate them into latitudinal bands. We call those segments. Right? So everything that we are attempting to do here is what the ZAR model actually is doing as well with their model is, can we reduce, our original data into smaller and smaller and smaller chunks? And just recall that the file name has a bunch of conventions, so you don't need to even open the data to know, the time that it belongs to, the version that it belongs to, etc. and etc. And this is just a reminder. You've seen that before. It is here, so if you want to come back to this tutorial, you have it there. Okay, I'm now going to go through the downloading process. Jessica and Amy showed to you that very nicely. But I put all the cells here, all the steps of what I've done to download the data that we're going to use here. So this is fully reproducible. And these are the steps that Jessica just showed to you using the iSpeaks downloading interface. Instead, what we're going to do, I already downloaded those data. It's actually Ben did. And we are going to use this folder, which is on your home directory on something called tutorial data, and then land ice applications, then Pine Island ATL06, right? So we're going to define our data home as that folder that contains a bunch of files. So here, the other cells are just iSpeak stuff that we don't need it for this tutorial, but you can run them. And here as well, display information. It takes some time here because I'm putting everything on the same cell. I'm pulling out some metadata information I want to see before downloading the data. This might take a little bit to obtain and then plot a map with the extent. Let's see how long it takes that. There we have. And here is our extent of our file. Let's zoom in. As Jessica pointed to you, nicely shows to you, okay, this is the extent of data that you are requesting. We haven't downloaded anything yet. And this is Pine Island. And this is a square box in there. Pretty nice. Okay, this is then the step where you actually download the data, right? So you can hit on that cell if you want. It's not going to download because it will check if your data folder is not empty, meaning it has data, it will not do anything. And we do have data there. All right, let's start with our processing here. Let's check that our data folder that we specified has the actual data files that we want. And so here what we are doing is just reading in that folder and printing the 10 first files from the list. And here you see that, home, Jovian, tutorial data, land ice applications, Pine Island, process, blah, blah, blah. This is one of those downloaded granules. We have a total of 191 data files, okay? So why do we want to reduce those files? Let's inspect one of those files. Let's take the first file. This is how we inspect one of those files. This is how data is organized in there. You have metadata, and then you have path to all sort of information. Then you have ancillary data. And then within ancillary data, you have many variables with all sort of information. Then we have the bean related data. And from each bean, you have a ton of information for that particular bean. So you can keep scrolling. You can keep scrolling. Now we have another bean. This is the round track 1 right. We're looking at the left. Keep scrolling. Round track 2. Round track 2 right. Round track 3 left, right. So, okay, these are all the beans. That's how the data comes in. And then in the end, we have more ancillary data, orbit information, quality assessment information, and so on and so forth. So as you see, what happened here, we want to provide you all the information that you might want. We don't know what the user wants. Now, what I do in my case, first thing I do is say, well, from all of these, what is that I want or what is that I need for my processing workflow is certainly a fraction of it. So let's do that. Next step, what we're going to do is to code up a single reader that does a few things. This is a very simple thing, but the idea is to give you something that you can build on top of it for your own application. So we're going to select just a few variables of interest. I particularly just want location, XY, time, the high dimension, and perhaps the error and some quality flags. That's all I want. So we are going to filter at read time some points using the quality flags and using, for example, some user-defined thresholds, and further using some bounding box. Let's suppose you downloaded a bunch of files from a very large bounding box, and now you want to reduce those files just for a single glacier, for example. You can do that. We will do that in this reader. We will separate the data into further smaller chunks, as I said. So how about we separate each individual bean into its own file now? That will allow us to do, for example, a very convenient parallelization of all our subsequent operations. All right, let's jump right to it. First of all, we need some utility functions for our reader. And here I have just 3 functions, very simple. We're going to use the very nice PyTorch library that Dave Sheen introduced to you on Friday, which is for reprojection of coordinates. We're going to use another library, pretty cool, which is called AstroPy, and we're going to use the time functionality in there. So it turns out that ISAT data points, they come with something called GPS time, which those are seconds elapsed since 1980s, right, continuously. So we want to convert that into something more meaningful for our analysis. So we're going to convert that to decimal years, for example. You can do any conversion you want. Then we have another helper function, which will just identify if a set of points within a file belong to an ascending or a descending orbit. Why is this important? For example, if you're doing crossover analysis, you want to cross ascending versus descending tracks. So know that here at read time, we are going to also create some additional information of our own and store it together with our reduced files. In this case, will be just an array that has ones if that data point is an ascending track, or zeros if that data point is a descending track. And finally, we're just going to wrap the projection, the ProAge library, into something even simpler. We just need here to pass from projection 1 to projection 2 the coordinates, and this will spit out the desired reprojection. That's simple. Okay, next cell is our reader. All we need for that, apart from the helper function, is the H5Py library and a NumPy, for manipulating bare bones arrays. Okay, let's start the function. This function is a readATL06, right? You can extend or adapt this for other products if the idea is the same. And it will take as input one file, an optional output directory. Where do we want to output, the reduced files, and also optional a bounding box if we want to filter. But those are just optional. Okay, just describing quickly, I separated this reader into 4 logical blocks or units where you can actually then on each of these blocks do your own stuff and grow this reader. First of all, we are going to traverse through every single beam. We have 6 of them here. And the first step, we loop, and for each beam, we pull out the information that we want. And this is the place where we're going to define the variables you want. In this case, just because I want to pull latitude, longitude, the height, the sigma of the height, the time delta, that we're going to see what we do with it, the quality flag telling me, data is good, data is bad, etc. Signal to noise ratio information, and some geophysical corrections that they are provided for you, like dynamic atmospheric correction, tides, these faults from the ISAT science team, they figure, let's provide the more additional geophysical correction as we can. You don't need to use them, but if you want to do a quick correction and check, they are there for you. And some other information, which are not necessarily, variables, but like reference ground tracks, that's very useful. And the time reference. So I said here that we are pulling the T, delta T. So this is time elapsed from a time reference, right? So we also need the time reference, which is there. All right, that's the first block, pulling out those simple variables. Note that you can reduce these to 4 variables if you like. You just want lat, long, height, and time. That's all you need to put in there. Okay, now second logical block here. We're going to filter, right? And we have a few kinds of filter here. If you provided a bounding box, which is nothing else that minimum longitude, maximum longitude, minimum latitude, maximum latitude, it will then only accept data within the bounding box. Otherwise, it will accept all the data that is in the file. And this line here is what it will produce, that masking, which is a combined set of criteria. Quality flags, we want only data that is of good quality. Then there is a user-defined threshold here. I also, on top of it, say, well, I don't want any height that is higher than 10,000 meters, that is 10 kilometers. I know that the highest point on Earth is Mount Everest, so anything above that is definitely a gross outlier, so let's remove it. And finally, here is the bounding box if you like to use it. So this step here, one liner, what we are doing, right? Let me go back a little bit, I forgot to mention. So we are creating a data dictionary structure here, okay? So we are going to store all these variables into a dictionary called data. So in this case, what we are doing is updating that dictionary with the data that only passed these criteria, okay? So we still have our data dictionary in there. Very convenient to manipulate data in this way. Third logical unit here is where we're going to convert time, separate tracks into ascending, descending, and reproject coordinates. So here we're putting together the reference time plus the elapsed seconds from that epoch, and we get back the so-called GPS times, as I mentioned to you. Then farther down the line, we want to convert GPS time into, for example, decimal years. Decimal years is something I can look at it immediately and know where I'm located in time. So we created this variable T year. Then this is our helper function, orbit type, that is separating each individual point into ascending, descending. And finally, we all use polar stereographic projection, either if you are south, if you are in Antarctica, north, if you are in Greenland. So why not we reproject all the coordinates and also save them in the file? We don't have to do this every time we read the files in. So that's what the third line does. And the fourth line, the fourth block is basically saving. Okay, let's save all those variables, right? We added those variables to our data, and you don't have to worry about this. This is just checking if the output directory exists. If it doesn't exist, we'll create it, etc. But here, very simple also. 2 lines of code to save all that data that we extracted from our original ISAT2 files to our reduced data file, which we are gonna, you have defined as an out file with your, so you have defined an output directory. If you haven't defined an output directory, we'll create one for you, I think with a called data. And what it's doing is say, well, and what is the name of the output file? Just, you can do whatever you want here, but I did say, well, let's use the original file name and let's add some information to let us know that we further processed that file. So that's what we did here. Let's hit enter. So this is our simple reader, extremely simple, as you can see. I don't think, yes, I don't think I hit enter on the helper functions, right? So go back, hit enter on the helper functions. right? So check that this square bracket here has a number, then hit enter again on the reader, and that's it. Okay, now we're gonna read a bunch of files. Remember, we had 190 files that we want to reduce. So, okay, the next question. What if we have, instead of 190, we have, 1,000? Can we do this in parallel on a very simple way? Well, we just, saying that we are trying to operate in a smaller chunks as possible. So here there is another library called joblib. Here's a link for you to go there and see what this library does. So what is very nice about this library is allows you to do embarrassingly parallel tasks. That is, tasks that do not depend on other tasks on a very simple way without you having to actually invade your code. You don't need to write a parallel version of your code at all. All you need to do is wrap your processing function or code into a single function that takes some arguments, and then you will run that through a parallel loop. That's all it does. So let's, okay, let's go here to inspect what we have in the folder. We have a little Python script here called system status that I have put there to you. I mean, this is a courtesy of Scott. Last year he provided that for us. You can run it through the command line. All that guy is doing is checking the available resources for us. So this guy here says that we have 8 CPU cores. Now, let's pause there for a minute. This is not actually true because we are running several users per node. Each node here has 8 cores. That is correct what the script is saying. But we all users, we do not have access to, we are sharing these cores, right? So now I'm gonna ask you in the next steps when we run this that you do not hit the cell. Let me run it first so I can maximize the use of resources, and then you can try it on your own. So this is how you do your parallel reading. Here we're gonna specify a different data folder as output, okay? And that lies on this share folder that you all have access to and is in your home directory. And before you run this, I ask you to put your last name there so you don't write on my folder and each of us do not clash trying to compete for the same space. So put data, write your last name. I put Paulo here. Then define how many jobs do we want. I'm gonna put 8. Unlikely we are using actually 8 jobs, but this is the beauty here. If you don't have 8 cores available, the library will adapt and use whatever is available. And then you have 2 options here. You can run your code in serial. Nothing will happen in parallel, so you haven't changed your code a bit. And that is if n jobs equal 1. Otherwise, it will go to a parallel loop. So let's see what happened. And here it is. It started running. It is reading in chunks using 8 or 4 cores, whatever is available, those 190 files. So this might take a little bit because we are not truly using 8 cores. Now, if you have a server with 32 cores, which you can do a lot, for example, this is very handy. So done to task in 3.2 seconds. Okay, let it run this for a little bit. And this is taking much longer than if I was doing this alone. So I suspect it's because many of us, even though we are not running this in parallel, we are using the nodes for our Jupyter Lab instances. So we are actually using those resources. So what it can be happening here is actually reading in serial because it doesn't have cores available. So if this takes too much longer, I'll switch to something else. Total to handle, okay. All right, let's skip this part because it's taking too long to read that. It's not running in parallel. So I did run this tutorial several times before, and it will run that in less than 50 seconds, actually, if you are the only person doing this. So we can come back to this later. You can run this on your own. There you have. Now they have the 56 tasks, right, out of 190, and it took 1.8 minutes. So if I was running really myself on 4 cores, this will take under 50 seconds to write the 190 tasks. Should I insist on here or should I go because I have all the files set down there? So we have 10 more minutes left for this tutorial. I think we are doing actually fine with time, so I'm gonna just wait a little bit more for that. Files, read, let me see what happened here. Yeah, actually, let's stop the kernel for this guy here because it will take too long. And I have files that we can further operate that are already processed. You can try this on your own later. So you can go to kernel, shoot down all kernels. And then we can go here and run cells above this guy here. So we're running the notebook from the beginning up to, you know, this previous cell in here. And we're going to skip the actual reading of the files because we don't have enough resources to do that. I don't think it ran there. Okay, let's go one by one. I think that is not responding the Jupyter Hub here. So
Fernando, I think in the top right, it says you have no kernel. So I think you shut it down, but I think you need to close and reopen the notebook to get the kernel back.
Okay, doing that right now. Boom, let me close the other guy as well. There, let's see if we reopen this. There, green, now we have the kernel, correct? So let's go quickly because the last part of the tutorial will give you some tools on how we can handle these large data files. Let's keep the I speak stuff here. Select, inspect the file, we don't need that. Okay, let's go to our reader here. We don't need that as well. Python, yes, we're gonna skip this part. Let's go to the last point. Okay, we have, you know, read all these files. Now they will look just like those variables containing those simple variables that we define instead of those gigantic structures. Now, how can we handle then now? Because if we still have, you know, thousands to millions of points. And on Friday, they've showed to you a few libraries to operate with, you know, small to medium sized data files. And here I will show you some other options for handling large to very large data files. One of them is Dask, and in particular, a structure called data frames within Dask, which mimics Pandas data frame, but allow you to do this with potentially millions of data points. And the other is called data shader, which is a quick way to plot, you know, millions of data points to have a quick look. It will render that in a smart way by aggregating data and by making the renders of small chunks and then building a static image that will display to you. Now, in order for this cell to run, you have to change the path to the files because remember, we did not read those files, so we are reading different files. So is that guy in there? And we are gonna extract from those files these variables. Those files were already there and they belong to a tutorial that will be presented to you, I believe, tomorrow. And those are HDF5 files as well, reduced in the same way that I showed to you, and they contain variables, and then the names for those variables they have many variables, but the ones I'm interested in is longitude, latitude, and elevation. Okay, so you have to uncomment and comment there. And then hopefully this will run. And this also might take some time. So here we are using this Dask data frame structure, and this will create a data frame for us. And on this line here, what we are doing is using this very simple HDF5 reader. Compare this reader with the one we created, because we have reduced our files. Now we can access every single of our files just with 2 lines of Python code, the name of the file and a list with the variables. And this guy will spit out a 2D array where each column is the variable that we want to obtain. So this is your reader from now on. This is very convenient. And on this line here, what we are doing is loading each of those reduced files into a Dask data frame, right? On a Dask does this very smart, and it loads chunks of data from this. And then in this other line here, very important, I don't want to have to deal with many high performance data frames. How about I link all these individual data frames into a single structure, and I treat that as having a single data frame with millions of rows. And this is what I'm doing here. You can concatenate Dask data frames. So let's inspect that file. So we have 2 giant files that you can inspect, by going through this address. And the data frame looks just like that: longitude, latitude, and elevation. These are the first, 5 rows. And how many lines or points do we have in here? 3, I think it's close to 20. Is that correct? 20 million? Yes. Right? 19 million points. All right. So we can handle that easily on a data frame. How cool is that? And this is nothing for Dask. You can have more than that. So let's skip that. If you wanna, for example, if you like to work with comma separated values, ASCII files, no problem. You will take your Dask data frame and save all that to comma separated files in a smart and fast way. You can try this later on. Let's go to the plotting to wrap up the notebook here. And also you will have to change something on this cell, right? Because we are reading, remember, we are reading different files. So now we're gonna use data shader, which allows us to plot these, 19 million data points, and just by using, a few lines of code. And we are gonna have first line, we just define the size of our image, and uncomment this line, and comment the following one. This is just changing because we are using different variable names. And I want to plot from this data frame, which is a Dask data frame, long and lat. And I want to have an aggregate on elevation. What this is doing is taking means over square bins. So it's actually digitizing all that stuff, but it's doing it on a smart way. It's not pulling all the data within each single grid cell. It's calculating means, chunks at a time, and in the end, taking the mean of the means and rendering for you that image. That's why it's very efficient. And let's see if it works. And there you have. Very quick. These are a representation of 20 million points. These are not 20 million points. These are tracks, you have repeat tracks going over the other. So, but you have like a digitized representation of it. And this is, I believe, Pine Island here, Pine Island rounding line. You have the floating ice, on the left. And this is the Pine Island trunk, and we're plotting high. So this is, terrain, and the slope, the gradient on terrain here. So quick and dirty way of interacting with millions of points. All right, with that, more or less, we finished the tutorial. Here in the end, just give you, okay, can you automate all this outside of a notebook, for example? So I'm providing to you a reader for ATL06, which does what I showed to you here and much more, actually. And you can think that this reader can also be a processing piece of code that you develop. So let's see what this reader has here. Type, read ATL06-H to see, and has many options. So you can pass options to your processing code. And I'm not going to run this here because, again, we're going to run into this problem of sharing resources. But then you can just type Python, your code, the input files to read, the output file you want your resources, and just say, I want 8 jobs. So this reader also, or processing code, if you made it, we'll do all these operations in parallel as well, just through the command line. And here, basically, just to end, if you want to, I think, no, we don't need to do that. That's to inspect the reader. You can do that on your own, but it's a fairly large piece of code, so it's going to pollute your notebook. But you can do it later. All right. So with that, I will end this notebook. I just, if you have downloaded some data to share data last name, after we are done with the tutorial, if you can please just go inside that and remove the files. And later on, you can come back and try this on your own. And finally, you have many, many applications, you know, much more than I showed to you here, in particular to operate with HDF5 files. How about we want, you know, we have 200, 500 HDF5 and we want to merge them into a single one, or we want to merge them into 10 other HDF5 files. And how about we have one HDF5 file, we want to split them. We want to split them in time. How about we want to split them in tiles? How about we want these tiles to have overlapping data? All this functionality now is ready for you to use on this CattleKit Python open source package. So check it out. And with that, I'm open to questions, and thank you very much.